Hey everyone, Dan from Voxel 51 here, and welcome to my self-driving workshop, How to Unlock More in Self-Driving Datasets. I got a lot of really great stuff to share with you today. A quick intro about myself. My name's Dan Gural, Machine Learning and Developer Relations at Voxel 51. I've been dealing with self-driving datasets for about 3 years now. I've seen all the new advents and what's coming in, and I'm really excited to share you what really is the frontier of self-driving datasets today. So let's just hop right into it. It really is all about the race for autonomy. Who is going to break that threshold to be able to safely release self-driving cars out into the world today? Let's look at how it's shaping up today. So first and foremost, powerful GPUs are driving innovation. This should be a shocker to no one that has been keeping an eye on the field. With more powerful GPUs, you can train faster, but not even more train faster, but you can also put a larger GPU on the car itself. Had the fortunate experience to go into some of these self-driving workshops where they're actually building the cars and see them pull out a spare tire and put in an entire rack of GPUs. So it's very, very powerful now compared to where we were previously for the algorithms that we can now run on top of these cars. This also makes it very easy for us to scale. We'll talk more about this scaling problem, but we need as many GPUs as possible to be training all the time. We don't want to sacrifice any time in the real world, so we always want to be able to train as much as possible, train new scenarios into our cars, and the bigger GPUs, the easier these GPUs are able to scale like they are today, the faster we'll be able to train that best model possible. Another thing that is kind of juxtaposition, it's very different compared to what we've been talking to, and not just the hardware, but the libraries are much better than where they used to be. I can tell you this personally, as building PyTorch 3D for this workshop from scratch C++ only took me 5 hours instead of what used to feel like 5 days to build these libraries, as they're very, very infamously hard to work with. However, as time goes on, these open source libraries are getting more and more support. Not only are they easier to work with, work across better versions and hardware, but they're also getting much more optimized, allowing these models to run faster and making the whole process and workflow better. So overall, GPUs are making workflows faster, more efficient, and overall easier to work with. On top of this, we just have boundless amounts of data, right? Really am struggling to find visual AI field just had as much sensor data as self-driving cars. We're not talking about gigabytes or terabytes. We're actually talking about data at petabyte scale. We have companies out there that have maps of entire cities. Look at Waymo's strategy of trying to get as much data as they can about cities like San Francisco. And this has led to hours and hours of drives that include multiple different cameras, radar, LiDAR, any amount of annotations that you've stored on these data sets. There's just an insane amount of data. And another thing that makes self-driving very unique is that it has some very top tier talent. And that top tier talent very often is behind closed doors. If you look at Waymo, Wave, Tesla, a lot of these top tier self-driving labs are doing the best work today. They have some of the best engineers that have years and years of experience in visual AI. A lot of this, though, as I've mentioned, has kind of been behind closed doors for recently for competitive advantageness and things like that. But until now, and it's not for your first time watching this video, until today, as a lot of this research has been published recently, leaders like Waymo and Wave especially are trailblazing in this field, allowing us to kind of get an insight into what makes their labs so good and what research they're pouring their resources in. The last thing I really want to mention here that's so exciting to me is how much self-driving is like a big gamble. If you look at the three giants right now, Wave, Waymo, and Tesla, in my opinion, they all have very unique ways going about how they're going to solve this self-driving problem. Wave is trying to do end-to-end solution where they're going to not teach a car how to drive in London, but they're going to teach a car how to drive anywhere, right? And be able to encounter any scenario. And can you build this world model inside of a car that will be able to drive safely wherever it goes? You look at a different strategy like Waymo, where Waymo says if you learn the city from every inch of the city, you'll be able to drive that car very efficiently there. And that's kind of their strategy for now, at least, going from city to city, from San Francisco to now more locations. Able to know that city top down is going to be able to allow that car to drive very safely within that city. great for any robo-taxi kind of structure. The last one here, Tesla, is very unique amongst the industry as they are famously cited for not using any LiDAR sensors, purely image-based. This is very interesting as it's tough to believe that without the proper depth estimation of these LiDAR sensors, they have enough context to drive the car safely. Tesla says, though, with their latest models and strategy, it's not needed. However, we have no idea who is going to be right. Everyone could be right. Everyone could be wrong. And it's all one big gamble about how self-driving is going to take place in society moving forward. And I'm here today to show you exactly how we can build the data sets to support self-driving use cases and to make sure that you're going to be able to have the best data going in whenever you get time to try your first self-driving model. So here's how we're going to outline it. We're going to start with some beginner techniques. We're going to go to advanced techniques, and then we're going to check out those expert techniques. I'm trying to bring you the latest state-of-the-art, no matter where you are in your self-driving journey. So we're going to start with some very basic things and kind of work our way up. There's a little bit of a racing F1 theme today, so I hope you guys enjoy it. But let's dive into those beginner techniques and look at curation, visualization, and dataset management. Before we dive in, quick word from Voxel 51. Voxel 51 is the lead maintainers of 51, the open source dataset management tool that we're going to be looking at heavily today. 51 is completely open source. You're allowed to load in any type of visual data, whether it's images, videos, radar, LiDAR, point cloud. And you can almost think about it as that dataset debugger for your datasets to make sure you're able to find all the issues in your dataset. If you don't know what a voxel is to a pixel. A voxel is to a video what an image is to a pixel. It's that volume element for the space time of the video. And what's with that 51? Well, the joke around the company is the co-founders had 50 bad ideas, and then they had 51. We guiding us through this? Let's hop in. Before we get started, if you have any questions, be sure to reach out to my LinkedIn. I'm always happy to answer any questions you might want to expand upon, as well as if you want to follow along on any of the code snippets I'm going to be showing today. They're all publicly available in my GitHub repo. Feel free to scan the QR code here to get to the GitHub page, as well as I will link the GitHub in the description in the video below. Thank you so much. And so let's hop in, starting with our beginner techniques. So when it comes to working with a self-driving data set, there's two main issues that we're going to encounter. One is that all this data is unstructured. We have no idea what the data is going to look necessarily when it comes in, especially whenever you're working with one self-driving data set to another. What this means is that they could be any number of sensors, maybe multiple different cameras, some on the front, some on the back, as well as you might have any number of LiDAR sensors, radar sensors. They might be in different sizes, different frame rates. We have to be able to kind of corral all this data in one place that's not going to fit nicely like our traditional tables or time series data. The other thing is that we're going to be working with data at a huge scale, right? We talked about that petabyte scale. Even for hobbyist projects, for someone that's just exploring self-driving, you're still going to be working with a large amount of data. So we have to organize this data to make it usable and make sure we're not getting kind of lost in the sauce in all the scale of the data that we're working with. That's where 51 is going to come to the rescue. 51 allows you to kind of build your data set for any shape or size that you need. You have 6 cameras that are going in, no problem. I'll be able to take those 6 cameras and load all 6 cameras light by side with annotations and whatever you're interested in, as well as those LiDAR radar scans, help you understand things like poor quality data, misclassifications, detections, or model mistakes, as well as help you understand where are the gaps in your data. If you haven't seen 51 before, it is very easy for you to visualize, clean, and curate any of your visual AI data. You can help find the hidden structure, run things like embeddings to understand gaps in your data set, as well as evaluate any of your models. It's all flexible, customizable, connected, and most importantly, open source. This is all to help bring transparency and clarity to the world's data. Nothing's going to hinder your machine learning workflows more than just poor quality data. And if you're not improving the data set, you're not going to be improving your overall performance. By putting data at the center of your stack, you'll be able to push those models to production way faster than you would if you're focusing on specific model architectures. New models come out all the time. Investing in your data is where it's at. So let's take a look at some grouped data sets. I'll show you an example of how to build a grouped data set. But to reiterate what I said before, a grouped data set in 51 is any data set that's going to have multiple samples for one group. When we say group, it's kind of imagine if you're the car, every time you're taking pictures in that timestamp, we want to be able to make sure we can see the left camera, the right camera, and the snapshot of that LiDAR point cloud all in one sample. When I move to the next time step, I should see the next camera frame and the next LiDAR scan. Being able to group this data set so multiple samples can become one grouped sample is very advantageous for us whenever we're organizing this data set. So before we hop into our next phase, let's take a look at the code on how we can build our first grouped data set. So I have this code posted online, as I mentioned. There'll be some minor changes as I point to my file locations, of course, and things like that. Just follow along if you want to at home with your own data sets. So we're going to be working with the new scenes data set in this example. If you're working with it, I highly suggest creating a Conda or a virtual environment to manage all the different libraries we're going to be installing. And then we're going to be using the new scenes dev kit, and make sure you upgrade that matlib to avoid an error. So once you want to ingest new scenes into 51, if anyone is unsure about which new scenes we're working with, is links into the GitHub. But just to show real quickly, if you want to just look up new scenes on new scene 51 to get a full example, but new scenes, click here for the link, go over to the new scenes data set. You'll see that we have downloads over here. It's going to ask you to sign in or sign up. I'm going to quickly log in very quickly just to show you exactly the data sets we're going to be working with. We're going to want to grab this LiDAR segmentation. We're only going to be working with the mini, so grab this US. We're also going to want to work with the mini for the full data set as well. So download these two files. It's 3.8 gigs and then a very small 0 gig file here for the LiDAR segmentation. You're going to want to unpack both of these into one location. And once those are there, we're going to be able to work with it. So hopping back into our code, if everything looks okay, once you've unpacked those files, point to the location of where they live, run this first block of code, and you should see this giant spit that says that everything has been loaded in. Check in all those different things, check in the LiDAR segmentation, make sure everything looks like it is as expected. And if it is, you shouldn't get an error here. If not, if you do get an error, just double check the file location. Make sure that you unpacked everything. Make sure that even things like a trailing slash can be an issue sometimes when working with this new scenes dev kit. But if everything works as expected, you should get a large spit out like this. So moving on, let's look at how we can load in our camera data. So everything that we're going to be showing here has two sides in 51. There's the SDK, which is what we're looking at first. And then there is going to be which we're visualizing our data. Once we've loaded in this new scenes dev kit, we can create our first 51 data set. We're going to call it the new scenes camera data set, which is just going to be only the cameras for right now. We'll move on to the LiDAR point clouds afterwards. And since we're making it a grouped data set, we need to define that when we start. Say that the camera front is our default picture, but we're going to make sure right before we add any samples that this is a grouped data set. So for loading camera data, the most important thing when it comes with working with self-driving data sets, storing all that metadata, right? That is the gold mine of our data set. We need to know exactly where it was from, which drive it was, what day it was, what the parameters are, any camera intrinsics or anything like that we're going to be needed, as well as annotations. We want to store all of that on top of our sample. So let's define how we can load for any single camera, all the different metadata as well as annotations. Keep in mind, we're going to have like 6 cameras on our new scenes data set. So this is going to be for any given one of the 6 sensors. So here we start by defining a 51 sample. It's very easy. Just point it to that JPEG, PNG, whatever it might be. And then for a group data set, just tell me if it's the front camera, the back camera, the side camera, or whatever it's going to be. That's defined in our sensor variable here. File path is also the file path to the JPEG here. From there, we're going to make sure to grab all the information about this metadata and annotations from the new scenes dev kit. So we do that with the get sample data. From there, we're going to make sure that we format that all properly. And then from there, we draw all of our bounding boxes. These are 3D bounding boxes. So we're going to have our front and back of the bounding boxes. And then we can append those using the 51 polylines cuboid function and then add it on. I know I'm kind of going through a lot of this fast. I highly suggest that you dive into this yourself to get more in details, and feel free to reach out to me if you have any questions. There's a lot to get through, but I want to just give you the highlights. So all in all, load in that sample, load in the metadata, and then draw the annotations on the sample. Make sure you're formatting them as 51 expects. Once we're ready to add these samples to our data set, we're going to define all the different camera groups that we're interested in loading in. 6 in this case. And then we're going to say for each scene in new scenes, and for each sensor in our group, which in this case is our cameras, we are going to load that sample, store all the metadata, and then add it to a list. Once we've gone through every scene, which is each time you drive your car, right? Sometimes you're driving in a downtown and sometimes you're on the highway. Those are going to be separate scenes. So for each scene, for every sample in the scene, as long as there's not another sample after, right? Because these are videos. So as long as the video is still going, load in all 6 cameras. Once we run this all together, we'll be able to view our first here. After you launch that, you'll be able to load this self-driving data set and visualize it. Luckily, have ran this beforehand, so we can visualize it right away. But here we can click in and kind of view any of our data set. We can see all the different angles of our car. So we have the camera front, the camera right, the back left, and we can see those polylines as defined by new scenes. You can also change from standpoint which camera you want to look through. And at any point, I can kind of scroll through my grid to kind of understand this. What you'll notice right away is that all of these seem to be very similar because they're all from the same scene. What's also very cool is that we can group this dynamically by our scene token. If we go here, order by our timestamp. What this means is I would say, hey, for all my samples in my data set, I want you to organize them by the scene and then order them by the timestamp. When I do this, I'm going to begin to a new view where I can see now all my different scenes. We can see some at nighttime, some in different locations. And now when I click into any of these, I will see all these different timestamps below hand, as well as all my different camera angles up here. We can take this even one step further and say, instead of looking at them like a paginated view, we can look at them as videos as well and see exactly the kind of playback in front of us. That way we're able to kind of dive into our data set just as our car would. Always can go into here, click at it, and you can always set this to behavior by default or whatever you're looking for. All depends on what you like to do. So I'm going to turn this off. This is our very basic understanding. One last thing I want to highlight. If you ever want to reset the view, feel free to just click on the view bar. But we also want to point out all the metadata that we stored, right? So we can see things like our calibrated sensor token, ego sensor token, timestamp, keyframe, all this kind of stuff that's going to let us help fetch more data down the line when it comes to training and things like that. So that way we can always store as much metadata as possible. Always feel free to change things like color options, where I can change from, instead of the field, the value. And now my polylines have gone from all blue because they're the cuboids to different colors depending on what class they are. You can also turn on and off different classes depending on which one you look at. So if you only want to look at cars or trucks or pedestrians, all of it is completely possible for you. So let's hop back into our slides, Willie. That's kind of the basic of our data sets, but we kind of want to move past that. We have things, advanced techniques. And as you can see here in our group data set, we have LiDAR scans. So how do we work with LiDAR in 51? Well, it's very easy. Let's hop back over to our Visual Studio Code and check out the point cloud data. We'll create a new data set, this time including all of our sensors. And for this one, we just have to define 2 new functions, one for LiDAR samples and one for radar. So how do we work with LiDAR sensors? Well, the first and foremost thing that I need to get out of the way is that LiDAR has to be stored .pcd. Not only does that have to be a .pcd, we're going to work with the Open 3D library here. A lot of times LiDARs come MPYs or other things like MCAPs. We're working with PCDs as it helps us visualize them. You can always rewrite them as I do them here. So here, I'm not just rewriting them, but I'm also going to be coloring them based on that LiDAR segmentation that we downloaded earlier. So we grab that LiDAR segmentation, we paint our points. Once we kind of load the sample, we can now paint the points, color it, and then save it back to a point cloud, being able to use it for 51. Now that we've cleaned up all those samples, we do the same thing like we did for the cameras. We're going to grab that sample data to grab all that metadata. We're going to create the sample. We are going to make sure we add any geolocations. We actually have the GPS coordinates for each one. And then we're going to add all of our 3D bounding boxes, just like before. Just note that these are 3D bounding boxes in 3D space. So unlike before when we were painting cuboids, we are now painting based off the X, Y, Z, and the width, length, and the height of the box. Once we have all that done, same thing for radar in this case. We can go back into our big loop here. Notice that we have the same groups from before, but now we're loading in our LiDAR and our radar as well. We're going to say for scene and new scenes. While our scene is still going, for every sensor in our sensors group, load in that data, store the metadata, and visualize it. Now, when we hop back into our data set, we can see the same camera samples we saw previously, but when we click in, we're also going to be able to get those LiDAR samples. Some quick things I want to point out right away. First and foremost, feel free, once again, to change those color settings if you like to whatever you want. Whenever I change it here, you can see now our 3D bounding boxes are colored not by the field that they're pushed into, but the class that they are. So we can see our trucks, our humans, our cars, and they match over here from our 2D samples. And the other thing to notice is that we don't have just 3D bounding boxes in our LiDAR, as you can see here, but we also have those LiDAR segmentations. Notice that these blue dots here are the road, green stands for foliage, orange is the building, red is this truck, and we have more as we look around. This is due to our LiDAR segmentations that we downloaded earlier, and it can be super helpful when you make a self-driving car model in the future. But what happened after this? Let's hop back into our slides to see what goes next after you've built that first basic data set. Let's move on to our advanced techniques. Leveling up starts with more information. Now that you have that data inside your data set, how can you get even more out of it? We mentioned how we stored all that metadata previously, but there's much more ways we can explore our data set outside of the pre-given metadata. The two most important ways that we can do this is that by generating embeddings and leveraging them, as well as applying pre-trained models. Let's explore how we can do both of these in our data set. How do these models help with us? Well, let's start there first. Well, there's a couple ways they can help us. When we talk about these models, what models are we talking about? Well, we're talking about zero-shot predictors. These are world models that have ways to detect things that are commonly found in real-world scenarios inside of your data set. Things like pedestrians, cars, and more can be instantly found inside of your data set without having to do human annotation with some level of confidence. The more strange of a thing you're looking for, the less likely you'll be able to accurately find it. But this is a really fast way to kind of instantly find things like traffic signs, pedestrians, and more in your data set if they're not already labeled. Another way that we can take advantage of some pre-trained models is by using depth estimation. Depth estimation allows us to find things like knowing exactly how far away each car are, as well as things like help determine what scene has a very crowded scene, like a city scene, versus something that's maybe a little bit more spread out, like a highway scene. We can also take advantage of embedding models, both 2D and 3D embedding models, which help us find similar samples and explore these unique samples to understand where our gaps in our data set are. Because the name of the game here is all about helping find more information for both data curation, as well as potentially feeding into a model downstream. By using these pre-trained models, we'll be able to extract more information out of our data set, find what samples are unique, and what samples we need to add more into to better cover the real-world scenarios our car will be driving in. Hopping back into our code, we can get down to the leveraging embeddings section and figure out how we can start leveraging these embeddings. First, the thing I'm going to do is flatten my data set. We mentioned that this is a group data set with many different sensors that you're able to include in them, but we can actually flatten this and create them not grouped and say, only show me the images in this case. This way we can then apply a model to all of our images instead of passing in a group of images to a model, which won't work in our case. This allows us to do things like compute embeddings using a clip model, as well as compute similarity using the clip model too. What does this actually turn out to look like for us? Well, let's check in our 51 app. Heading over into our 51 app, we can head over to our embeddings panel, which can be opened using this plus button. Just head over to this plus button, select the brain key, embeddings viz, split them, and I'm even going to be able to color them by different metadata stored on my dataset, such as, for instance, the scene token. You can always adjust these to make it a little bit more visible, increase the sample size on the grid, or whatever you're interested in looking at. So now that we have these embeddings grouped, we can actually see the different layout of our dataset. How do I know this? Well, I can grab any of these points on my dataset in the embeddings grid and see exactly how they're related. You can see if I grab this cluster over here on the right, we're going to find a bunch of nighttime samples that are all related. If I grab a different cluster, such as this cluster down here, we'll find that these are original scene that we were looking at previously. This helps you understand different groupings in your dataset, as well as potential outliers. We can notice that this one is only looking at this building the entire time, for instance, so it's not super interesting for us. As well as we can grab this cluster up here and see what's going on and find that this looks like a pretty standard driving scene. The most important thing to understand about embeddings is how it helps solve some of the most crucial parts of self-driving datasets. Let's go back to that petabyte scale that we were talking about. Given a large amount of data, we're not going to be able to feasibly annotate all of our data that came off the car, right? Nor does this really make sense. One, it's too expensive to annotate all this data. It's expensive to get human annotators. You might have to do more than one annotation per image to make sure that there's a quality assurance, as well as it's just lots and lots of data to work with. But when we think about the problem, it doesn't really make sense, right? Because we don't need all the data to get annotated. We actually only need data that we haven't really seen before to be annotated, right? Because the most important thing for our self-driving data set is to be able to represent the different scenes that our car will encounter. If we have 40 times the amount of scenes that are driving in a city, for instance, especially if we think about like every time I turn on the camera for the car to start a new scene, if I'm pulling out of the same garage and then driving down the same road to the highway, well, I don't need that part that I've seen 100 times to be annotated 100 times. This will only duplicate our data set and make it unbalanced, not letting our car train on the things that we care about most, which are unique outlier scenarios that we want our car to be safe in. By using an embeddings grid, we can actually see this different distribution of our data set to understand exactly where we maybe need to add more samples in and what we want to get annotated. If we look closely, we can see the coloring of all of our different points. And we can also notice that another interesting feature here is that each color represents different scenes. We'll notice some scenes, such as this blue scene here, have very clustered samples, where all the cameras on the car seem to be looking at very similar objects or scenes or locations, whatever it might be. However, we have different ones, such as these clusters up here, where in this case, the cameras are looking at very different things. We notice that sometimes it's looking over a bridge on a river, but just a different camera on the same car in a different scene is looking at a building or a faraway building, right? And this can also help us find edge cases where in some cases, our cameras are looking at all very similar things, and in some cases, our cameras are looking at very different things. This is just all to help us understand which ways we can design new evaluation test cases, scenario test cases, as well as figure out, given the data set distribution, what data we need to go get annotated to provide value to our next model training run, as well as when we go think about what data we need to go procure the next time, can I fill in the gaps of my data set here to have a well represented world scenario. We can also look at the similarity search that I mentioned before. Using similarity search is very easy in 51. I can just click on this little magnifying glass. I'm going to say, find me all the traffic signs in my data set. And this is going to scour our entire data set, create that new clip embedding, and compare it to find the 25 most similar ones. And then from here, we can see all these different traffic signs in our data set to help us understand exactly how our model is doing on all these ones. If we trained a model on finding all the traffic signs, we better be able to find all of them given our clip search here. This is just one way that you can help curate, dive in, and explore your data sets by leveraging embeddings. However, there's plenty more ways we can use them, such as things like finding your most unique samples in your data set, finding likely label mistakes, being able to find your hardest samples, as well as your most represented sample in your data set. All these are located inside the 51 brain in order to take more use on your data sets. But however, we can also use the model zoo. This is those pre-trained models that we were talking about. And we can look at things like SAM2, which recently made headways coming out of Meta as one of the most popular models right now, as well as we can use a depth estimation, depth anything, in order to store our depth estimations on our data set as well. We're going to do this on only our first 24 images just for the sake of this demo, as it runs quick. And you can also choose to store the map in memory like we're doing here in SAM, or you can save the mask output to a directory on your computer. So heading back in, let's check out what these look like exactly for us. You can check out that we're now back and we can click into SAM2 to turn on that segmentation mask, as well as our depth anything. So looking at SAM2, there's two ways you can run SAM2. You can either prompt it with key points and bounding boxes, or you can tell it to run wild as I've done here. So here you can see that sometimes it segments the entire car. It's always getting the whole sky, which is actually going to be super useful in the future, as well as drivable areas, cars, and many more things that you can prompt SAM2 to segment. Looking at our depth estimation, we can help understand which things are far away and which ones are close. We can always switch that coloring to help us understand more. And we can see things like we would expect, like, well, the road in front of the car is much closer than the road further away from the car. We can also see that the truck is a little bit closer, as well as some other things like the trees that are lighting up. This helps us understand a little bit more of our data set, as well as we can apply this to all the different cameras on our data set, as we see here, helping us understand more insights into our data and be able to feed more things into our model downstream, QA annotations, and more. All this comes completely out of the box in 51, all open source, and you can take advantage of it today on any of your data sets. However, there's even more that we can unlock in our self-driving data sets. Everything that I've shown you so far is very advanced and kind of shows you what state of the art can look like. Small hobby project, but what are the labs out there doing to kind of take it to the next level? So we're going to talk about the expert techniques. This is only for the state-of-the-art use cases and how they're really taking self-driving to the next level. So we have to start here about what are one of the largest blockers for self-driving. Pause the video maybe for a second and think about if you can answer based off our presentation so far, what is going to be the largest blocker for self-driving? Well, the answer is going to be time. We don't have enough time to train all these models. Also, I don't have enough time to train a model, push it onto the car, and drive the car around the town, see if the car is going to knock into anything. If it does knock into anything, I need to stop the car. I need to bring it back, find the scenario that it knocked into something, retrain the model, reload it back onto the car, drive back out there. I need to tell grandma or whoever it was to walk back in front of the car, hit you last time, and hopefully it hits the brakes next time. And you can just begin to see how this is a huge mess. So how can we overcome the obstacle of simulating, testing, and being more efficient with the time that we have? Well, the answer is going to be, as I mentioned, in simulation. We can see test scenarios here, which we want to find in the real world and kind of reimagine a simulated environment. We can see here that we have this zebra cross, as we call them. We stop here, we wait properly for both pedestrians, and then we continue to go. But what if my car didn't stop? What if I mentioned there, like I mentioned previously, that it bumped into someone or blew right through the stop sign, the zebra cross from the get-go? How do we train our model to make sure that it's correcting from this scenario? Well, if we can't control time, we're not going to be able to stop time and tell the car to run that scenario again in real life. Well, then we just need to control the world. How do we do this? Well, we need to generate and simulate the world ourselves. So what you're looking at right here in this video stream here looks very similar to that new scene that we were looking at previously, but everything you're looking at here is actually 3D generated sample. Yeah, that's right. Everything you're looking at here is actually not real footage. It's generated through a model. So once we have these models that can generate the world, we can now head into the next frontier, right? And this is all what it's about. So if you want to learn out how to do these 3D generated models, I do have a example, the code here. Head over to our expert techniques, and we're going to be taking advantage of Drive Studio, one of state-of-the-art open source projects that allows you to leverage multiple different types of self-driving car data sets, multiple different types of models. And this is all using the brand new Gaussian Splats. Gaussian Splats are really exciting in the world right now. I'll kind of talk about it in a second, but it helps us kind of load in these scenes, generate the 3D simulations that we can create, and help us run them. So if you do follow the Drive Studio setup correctly, we'll be able to load in and visualize that data from 51. Just a quick note here that the groups all have indexes now. From there, we're going to load it in. This is only for the first scene of new scenes, and very similarly, we're going to say for each group, for sensors, load in all these masks we created. How does this work? Well, we actually first generate all of the masks. I'll show you what that looks like. So once we push the 3D, there's two main steps here. First step, as I mentioned, we need to make sure that we can kind of segment all the different things in our data set. So let's turn off those original cuboids that we were looking at here, but we can look at this picture. There's a lot going on here, so I want to dive into it. So first thing, we want to segment out the sky. Why is that? Because maybe in my simulation, I want to make it nighttime or daytime or snowy or sunny or cloudy or rainy or all these different scenarios. First and foremost, I need to be able to take out the sky so I can drop in my own sky later. The second one that we're going to look at is all of our masks. So we can notice here, we have a lot going on. I'm going to turn them on one by one and kind of show you what one is which one. I can also kind of spread this out here so we can see exactly what we're looking at. So first, we're going to have our dynamic mask all, which simply just masks in a very large and confident way all the different objects in our data set. Either cars, people, whatever it might be. Just I'm super confident that there's some type of object inside of these boxes. We can then try to do a little bit of a finer job to make sure that we're finding all these kind of things, but as you can kind of see, we don't always have the best success. We're missing a bit of the truck here. If we move along some of our cameras, we do much better on things like people here, as we can see, but we still miss things like umbrellas. Then we just want to be able to split this same process up into humans, fine and broad, as well as vehicles. Back to this one. Now that we have all these masks in our data set, what do we actually do with them? We have all these new masks that we generated. Well, I want to create this 3D world, but I want to make it as customizable as possible. And in order to do so, I actually need to remove anything with a mask on it. Why, you might ask? Because I want to be able to drop my own cars in, my own sky in. I can even take the ones I've removed and move them around, copy and paste, whatever I want to do in order to kind of capture that scenario that I pulled from my footage, from my car training, from a simulation, to be able to kind of change it just ever so slightly. That way, from instead of having one data point, I can then augment and create synthetically 20, 50, if not 100 data points that are very similar to the one that we started with. And this all comes from real world footage. We're prompting in first, and then how can we augment it from there? So once we've segmented all of these away, we can head over to our final output here, which is going to be our Gaussian Splats. So we can watch this video here. It's completely 3D generated. As we can see, we've removed that sky. We've actually even removed a lot of the cars that were on the road previously, as well as people, pedestrians that were walking on the sidewalks, just so we can kind of, as I mentioned, drop these in however we like. We can even see some ghosts past here from our video. But why are we using this? Why Gaussian Splats? Maybe you're familiar with some of the other ones, such as NeRFs. Maybe you're familiar with other 3D formats, such as PCDs, of course, but also things like PLYs, OBJs from the past, traditional 3D work. Well, Gaussian Splats are really exciting for all the 3D spaces, including self-driving, because of how efficient they are. Yes, NeRFs are very sharp and accurate, but they're also very slow and create high stress on the GPU. By creating Gaussian Splats, you're able to run efficiently and faster, saving that time that we mentioned before, by running anywhere from 20 to 50 times faster than a traditional NeRF. And using Gaussian Splats, we can create these test scenarios, simulations, and more that help us train these models. So here you can see all of our stuff here. We can see where we've removed all of our people, where we removed our cars, and some of the generated outputs here that we're able to take advantage of. When we get to the final output here, it's all going to come down to the Gaussian splat that we generate, right? This is where we are going to push our car into a test simulated scenario. And here is the output that I was able to run on my computer. It is, of course, not the best as I don't have the biggest GPU in the world, but it's still awesome to see how from a single video, this is only taking a single camera feed, that front camera in, how I'm able to generate a pretty good 3D world that I can start creating for a simulation. So this is how our top tier self-driving cars labs are taking advantage of Gaussian splats to level up their workflows, able to train much more faster, more efficiently, and be able to create these new simulated scenarios that can cover more real-world cases. However, there is still a flaw here, and this is where the next frontier, where the field is going from here. Why are splats not the full answer? Well, first and foremost, they're just hard to work with, right? It's new for a lot of people. We're still learning it. But more importantly, just because I created a 3D simulation of my world doesn't mean I can actually simulate a car inside the Gaussian splat right now. There's still a lot of work to be done from what I just showed you. I still need to drop those new cars in and place them wherever I want. I need to add new weather in. I need to be able to drop my car in as a simulation there and be able to drive it through and make sure all the sensors are simulatively working correctly. And it's just a lot of work that, as a computer vision or visual AI engineer, I'm just not experienced with. I've never worked with tools like Blender, video game engines, or whatever it might be, to be able to kind of take this to the last mile. It's also very hard to correct. You can notice there's a lot of holes in my Gaussian splats. There is a level of accuracy that is acceptable to be a little bit less than ideal. When it comes to training these self-driving cars, I say that to mean that if the Gaussian splat's not perfect, it's okay. We still have found that in recent research, the car will still work and train very accurately, the same way we train in real life. However, the moment we start having very large artifacts in our Gaussian splats, then we're going to start training the model on things that don't exist in the real world, and then we're going to have some significant issues. Gaps in your data can destroy your performance. So just like we just saw everything previously with dataset management, curation, data quality issues, all that kind of stuff, we want to make sure that we're still having good dataset practices with these Gaussian splats. They're not an end-all, be-all solution. However, how can we make it better? Well, we said if you can't control time, we want to create the world. Well, if you can't create the best world, how do we do that? Well, we're just going to prompt the model to do the rest for us. So we're looking at the Gaia 1 model here from Wave, which is one example using Gaussian splats, where given a video input from multiple cameras, as we just did previously, I can now generate these simulated scenarios, augment them just through text prompt. What do I mean by this? Well, let's look at the next example here. Keep an eye how all these videos are going to start from the same point, just because they're all prompted with the same input video. However, we're going to take different actions. Sometimes someone's crossing the road, sometimes the car turns left, sometimes we stop, and sometimes we keep going. We can change the weather in these scenes, and it's all using just a text prompt to help generate these multiple possible futures. This helps speed up the simulations, helps speed up the dataset creations greatly, help you save on that time, helping remove the amount of real-world test runs that we have to create to train the best self-driving model. Even if it's impossible to capture all the scenarios in real life, we can help at least kind of make up for it in the simulated world. This is some of the greatest stuff that's coming out right now. This came out, I believe, in CCV of last year, and there's even more and more progress being made. So it's a very exciting field to watch on how these data sets are being created. So as I mentioned, we can always have the code and the LinkedIn for everything that I showed you here today. If you're interested in it, be sure to hop over to my GitHub, star the page. If you have any questions about the work that I showed here, an issue that you ran into, anything like that, be sure to hop into my LinkedIn and let me know if you have any questions. Drop a follow if you're interested in more content like this. I'll be sure to post more. I want to thank everyone for hanging through this workshop. It's going to be such an exciting world with self-driving. I'm so excited for what 2025 has in store. I hope everyone has a great day and get out there and build the best data sets you can.